Okay, so today we're going to talk about arithmetic. This is our last topic, arithmetic and geometric sequences. Okay, so here I have a sequence of numbers, 7, 3, -1, -5. Okay, and we want to describe this sequence. That is, I would like to be able to write the nth term for any for this sequence and be able to generate any term for it. Okay. So now what we have to start doing is we have to start looking for patterns. We know that a sub 1 is equal to 7, and that a sub 2 is equal to 3, and that a sub 3 is equal to -1, and a sub 4 is equal to -5, and a sub 5 is equal to -9. So is there a pattern that would get me from one number to the next? So the simplest thing for us to notice is that 3 is equal to the previous number minus 4. Now -1 is equal to 3, the previous term, minus 4 as well. Let's see if this continues. Is -5 -1 minus 4? Sure it is. Is -9 the previous -5 minus 4? Yes. So what we see here that's common is that we're subtracting 4 from the previous one each time. Now, so a way we could write that then is the nth term will be, okay, so let's also remember this. So we're looking for the nth term somewhere in here, and then the next one would be n plus 1, and the next one would be n plus 2, etc., etc., etc. Now I could say the one preceding n is n minus 1. So we've seen here that what we're doing is that we're taking the previous number, a sub n minus 1, and we're subtracting 4. Now, we could also think about it this way. This is 7, our starting number, plus 1 times minus 4. This is 7 plus 2 times minus 4. This is 7 plus 3 times minus 4. And this is 7 plus 4 times minus 4. Alright, so again our minus 4 is in there, and it's just, now we've defined it in front of the first one, a sub 1 plus, now we have to figure out how to call these, and then times minus 4. Okay, so what is it that we're going to call these numbers? 1, 2, 3, 4. Well, if I look at them in terms of n here is 5, this one's 4. N here is 4, this one's 3. N here is 3, this one's 2. N here is 2, and this is 1. So really, those numbers are n minus 1. And this is another way that I could describe the nth term. Okay, so this is the pattern. Okay. So what happens here is one special sequence is known as the arithmetic sequence. Okay. It's a sequence in which the difference, meaning the subtraction, between two consecutive, that is, one right after each other, the two consecutive terms is constant throughout the sequence. So the constant throughout this sequence is the minus 4. So anytime we want to generate an arithmetic sequence, then what we can use is the nth term will be equal to the first term plus n minus 1, as we see here, n minus 1, and minus 4 is that common difference, so we'll call that d. So knowing this, we're going to be able to generate many different arithmetic sequences. Okay. So now, let's say that I need to find the first term and the common difference of an arithmetic sequence whose second term is 19. Okay, so I know that a sub 2 is equal to 19, and whose fourth term, so a sub 4, is equal to 25. Okay. Now I have to keep in mind that a sub n is equal to the first term, which I don't know, times n minus 1 times the common difference. So really, if I find the first term and the common difference, I can generate this entire sequence. Well, I don't know much right now, but I know this. I know a sub 3 would have to be 19 plus the common difference, whatever that would be. Okay, so the previous one plus the common difference. And the fourth one would have to be 19 plus 2 times the common difference. Just as I'm generating this. But luckily I know what a sub 4 is. So a sub 4, so 19 times 2 times its common difference is equal to 25. And now this is just a simple equation to solve. So 2 times the common difference, subtracting 19 will be 6, and dividing by 2, the common difference must be 3. So now I know what D is. How am I going to find a sub 1? Well, if a sub 2 is 19, a sub 3 is 19 plus D, then a sub 1 must be equal to 19 minus the common difference. Or that a sub 1 is equal to 19 minus 3, which is 16. So now we can say then from here a sub n is equal to a sub 1, which is 16, plus n minus 1 times the common difference, which is 3. And now we'll just simplify this. We can distribute this through. So the nth term can be written as 16 plus 3n minus 3, or the nth term will be written as 16 minus 3 is 13 plus 3 times n. So our arithmetic sequence now starts as 16 is our first, and then 19, and then 22, and 25, and 28, etc., etc., etc. Now let's do it a little bit differently. Let's say this is our sequence, 12, 6, 3, 3 halves, 3 fourths. Okay? And let's say we want to find the next two terms in this sequence. Alright, so let's find out what we have here. We have a sub 1 is equal to 12, a sub 2 is equal to 6, a sub 3 is equal to 3, a sub 4 is equal to 3 halves, a sub 5 is equal to 3 fourths, and it continues. Well, what we can notice, let's look at consecutive. 6 is 12 times 1 half. Now if we compare these two, 3 is 6 times 1 half. 3 halves is 3 times 1 half. And 3 fourths is 3 halves times 1 half. So what we're noticing here is that there's a common number again, it is 1 half. It's common between any consecutive terms in the sequence. And now it's not that they're being added, they're being multiplied. So I could write the nth term here as a sub n is equal to the previous term, so a sub n minus 1 times 1/2. Now let's look at this a little bit differently. This is 12 times 1/2. But 12 times 1/2 is 6. The next one is 6 times 1/2. So I could rewrite 6 as 12 times 1/2 times the additional 1/2. It's 1/2. So this is really 12 times 1/2 squared. Okay. 12 times 1/2 is 6. Okay. Now here I have 3. All right. Well, this is equal to 3 times another 1/2. So this is really 12 times 1/2. Now here it was squared, plus one more would give us cubed. In this case, we'll find out that this is 12 times 1/2 to the 4th. So another way for us to write what generates this, a sub n, is equal to 12 times that ratio 1/2. Now the question is to what power? Okay, so again we'll look. N here is 5, this is 4. N here is 4, this is 3. N here is 3, this is 2. So really it's to the n minus 1 power. So this describes a second sequence. It's called the geometric sequence. Okay, and that happens when there's the ratio of two consecutive terms is constant throughout the sequence. So that is the ratio as a division. If you take any two terms, a sub n and divided by a sub n minus 1, you're going to get this common ratio. So in this case, our common ratio was 1/2. Okay. This is known as the common ratio. And what this tells us then is that if we want to generate anything, we can take a sub n to be, from above, 12 was our first term, so that's a sub 1 times r, which is our common difference, to the n minus 1 power. This will generate geometric sequences. So now let's see if we can distinguish between these two. So let's say our sequence is 3, -6, 12, -24. Okay, we want to find the 10th term. And for us to do this, we need to know if this is geometric or if it's arithmetic. And it could very well be that it's neither. Well, if it's geometric, we're going to have to take the difference between the two. So the difference between here, -6 minus 3 is -9. 12 minus a minus 6 is 18. So clearly this is not geometric, or this is not arithmetic. Okay. No common difference. So that means not arithmetic. Okay. Well, let's look and see here. If I wanted to get, now is it geometric? If I wanted to get from 3 to -6, I would need to multiply by -2. From -6 to +12, I would need to multiply by -2. I'm sorry, this should say 24. 12 times -2 would get us to -24. So there we have a common ratio of -2, and so this is geometric. Okay. Now, for the geometric, to generate it, it's a sub n is equal to a sub 1 r to the n minus 1. Okay? So in our case, a sub n is equal to, the first one is a sub 1, which is 3. Then we multiply that by r, the common ratio, which is -2, to the n minus 1 power. Now notice this n minus 1 is only attached to the common ratio, and then we multiply by 3. So follow the order of operations. We'll need to do exponents first and then multiply. Okay, this is not negative 6 to the n minus 1. It is 3 times negative 2 raised to the n minus 1. Alright, so now that we know that, we can find the 10th term. So a sub 10 is equal to 3 times negative 2 to the 10 minus 1. Which in our case will be, we could simplify this to negative 2 to the 9th. And so this will be good enough for a sub 10. If we could simplify this, we would. 2 to the 9th is a little bit large. Not impossible, but a little bit. Okay. So that's really all that distinguishes the arithmetic and the geometric. One is if it's a common difference, then it's arithmetic, and if there's a common ratio, it's geometric. And then we can just use our generating functions to figure out what our 10th terms would be, or whatever terms. So what about these limits, right? So let's examine the limits of the arithmetic sequences, okay? Now, because everything is in the arithmetic sequence is with this common ratio or common difference, that is what's going to affect these things. Now, if the common difference is greater than 0, then you're adding a positive value and you just keep adding positive, positive, positive. So if that happens, then the limit as n goes to infinity of that sequence will be infinite because you're adding a positive value all the time. Now, if it's less than 0, that is negative, you're subtracting all the time, then the limit as n goes to infinity then will be negative infinity. Okay. So we have 3 cases where the difference is greater than 0, then you're approaching infinity. If it's less than 0, you're going to negative infinity. Our third case is what happens if our common difference is 0? Okay. Well, if the common difference is 0, then this term goes away, and we're simply left with a sub 1. So if the difference is 0, then the limit as n goes to infinity of your sequence will be just your first term, a sub 1. Okay. Alright, so now we can ask ourselves, what is it about this limit? So I guess I should rewrite this. So a sub n is equal to 1 plus 2 times n minus 1. Okay. And we're asked about this limit. Well, d is equal to 2. Okay, from here. This is a sub 1. This is d. Now 2 is greater than 0, so we're consistently adding more and more and more. So we can say then that the limit as n goes to infinity of the sequence will go to positive infinity. Okay. Now on the other hand here, we have to look at 3 minus 2n. Okay. So a sub 1 in this case is 3, and our common difference here now, we have to be careful. Let's remember, we have to take this to be with the negative. So our common difference there is negative 2. And that's why this one will be approaching, the limit will be equal to negative infinity. Okay. And this third one illustrates where d is equal to 0. Okay. So here, this is just the constant sequence. F of n is just equal to 715, 715, 715, etc. Okay. It is arithmetic, because the common difference here is just 0. I'm just going to add 0, add 0, add 0. Okay. So that is why, then, if you look at as n goes to infinity, this is just going to stay at 715, which is the first of the sequence. So it's really that f of n could be written as 715 plus 0 times d. So the limit then of as n goes to infinity of f of n is just equal to its first term, 715. Okay, now let's examine the geometric sequences, okay? So, one way for us to do this is so let's say we have a sequence a sub n that's equal to 2 times 1/2 to the n minus 1. Okay, this is geometric. And now we're wondering, what is the limit as n goes to infinity of a sub n? Well, we could just start looking at the sequence. So here our sequence, the first would be 2, then 1, then 1/2, then 1/4, then 1/8, etc., etc., etc. So we can see that as we let n increase, these numbers are getting smaller and smaller and smaller, and it is decreasing and it's approaching 0. Now, let's consider a sequence that's very close to it. What if it was 2 minus 1, 1/2, minus 1/4, positive 1/8, minus 1/16, etc., etc., etc. Now, this is an alternating sequence. So is this geometric? And if so, what is R? Okay, well, this is negative 1/2. This is negative 1/2. This is negative 1/2. Between here and here, negative 1/2. That is 2 divided. Negative 1 divided by 2 is negative 1/2. Negative 1/2 divided by 1 is negative 1/2, etc., etc., etc. Okay. Thus, then we can say, even though these are getting smaller and smaller, and that's one of the reasons why we can do this, even though it's alternating, because the absolute values of these are getting smaller and smaller and smaller, approaching 0, we can say then the limit as n goes to infinity of 2 times negative 1/2 to the n minus 1. This is the sequence. Well, that's equal to 0. Okay, let's try another one. What if we have 5, 10, 20, 40, 80? Okay. This is geometric. We're going to be multiplying by 2. Okay. By 2, by 2, by 2, by 2. Okay. So what is the sequence, or the generating term for this? Well, a sub n has to be equal to the first term, a, times the common difference, r, times the common ratio, r, which in this case is 2 to the n minus 1. Now what's going to happen in this case? Well, as n increases, this is going to be 2 to the 3, 4, 5, 6, 7, 8, 9, 10 power. And these are increasing without bound, and 5 times that certainly will. So if we had to look at the limit in this case, or this geometric sequence, the limit does not exist. It's infinite. Well, okay, instead of saying it does not exist, this we could actually label as infinite. So it is a divergent series, but we'll label that as infinite. Okay, as opposed to now let's look at let's look at this one. If f of n now is negative 5 to the 2 to the n minus 1, now if we look at the limit as n goes to infinity of f of n, well, now we have the opposite problems. Okay, again, this will increase without bound, okay, to positive infinity, but we're going to be making everything negative, so in the end this one's going to negative infinity. What about this sequence? 1/2, negative 1, 2, negative 4, 8, negative 16, etc., etc., etc. Okay. Is it geometric? Absolutely. The common difference here is negative 2. I'm multiplying by a negative 2 each time. Okay. So our common, or not difference, our common ratio here is negative 2. And it's alternating. But what's happening here? So a sub n has to be equal to the first term, which is 1/2 times the common ratio, negative 2 to the n minus 1. So now what is our limit as n goes to infinity of a sub n? Well, the positive nuns, if we look just at the positive, we go 1/2, we go 2, and then 8, and then 32, etc., etc., etc. So these are going to positive infinity. If you look at the negative ones, 1, negative 4, negative 16, etc., etc., these are also decreasing now, and they are decreasing without bound. So what's happening here is that if we were to do a quick sketch, it would be 1, minus 1, this would be up here, this would be down here. And so you can see in this way that as n goes to infinity, the sequence is not increasing without bound directly, it's alternating back and forth. So in this case, this is one where we certainly say that the limit does not exist. Okay. Let's go back to our tricky one. Remember the f of n, it was just equal to 715. So we said that this was geometric, or it was arithmetic, because it was just the remember it's just 715, 715, 715, etc., etc., etc. So is this geometric? And in this case, this sequence is actually geometric. Yes. In this case, our common difference is equal to 1. So we could write the nth term of this as the first term, 715, times the common ratio to the n minus 1, which is just 715. Okay, so in this case, it is both geometric with a common ratio and arithmetic with a common difference. Okay. All right, so what can we say about these limits, then, of the geometric series? Okay. Well, again, it comes down to certain cases. All right, so if, for example, it'll depend on what's happening with R. Sequences. Okay, so remember it's generated a sub n is equal to a sub 1 r to the n minus 1. All right. So we have case 1. If r is less than or equal to negative 1, so an example of that was when we had 1/2 to negative 2 to the n minus 1, then what we saw here, and it will be true for all, then the limit as n goes to infinity of a sub n does not exist. Now, if r goes in between negative 1 and 1, then the limit as n goes to infinity of this sequence a sub n would be equal to 0. So an example of that was 2 times 1/2 to the n minus 1. But it would work if it was negative 1/2 to the n minus 1 as well. Then we consider where r is greater than 1, but our a sub 1 is negative. So in that case, negative 5 times 2 to the n minus 1. What we said then was that the limit of these sequences will be equal to negative infinity because the a sub 1 is forcing, while this is increasing without bound, the negativeness will force it to negative infinity. And the last case is where r is greater than 1 and a sub 1 is now positive, then the limit as n goes to infinity of a sub n will be equal to infinity. So in this case, positive first value, positive ratio, greater than 1. Okay, so that should get you through your homework. If you have any questions, send me an email.